This is the tricky bit. Note that part that I crossed out. Can be negative or positive. Acceleration can be negative or positive. So let's look at a few more graphs. Let's do this. If this is, well, actually, let's do this. Ooh, what did I just do to the y-axis? I allowed it to go negative. Huh. So if I'm looking at a position time graph, we said that delta x was just your change in position. So if this is 0 and this is positive 1 and this is negative 1 and this is, and I'm not counting, so don't make fun of me, positive 10, negative 10. If we start at positive 4, so we start at positive 4 and we end at some time at negative 4, what's our displacement? Negative 8. Because x final minus x initial equals delta x, and we have negative 4 minus positive 4, so we have negative 8. We're going to assume meters here is our delta x. Awesome. So what if we look at the velocity for that? Let's see, 2, 4, 6, 8. Okay. Well, actually, no, I screwed that all up. Oh, well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, perfect. Okay. So from t equals 3 seconds to t equals 10 seconds is how long it took me to do that. So my average velocity for that, well, that's just delta x over delta t. That's negative 8 meters over 7 seconds. Could have made the math easier on myself, couldn't I? So don't you dare give me 8/7. I'll beat you with a physics stick. It's like 1.14 something. Slightly over 1 meter per second, sig figs, because I'm doing a crappy job here to 1 meter per second. Well, what if we look, resume. So we agree, and if we look at the slope of that line, the slope is negative. So we agree that the velocity is negative. All good so far. Excellent. Excellent. Velocity time graph here, badly drawn, but, you know, that's what you get. So let's say I start off with 0 velocity. I increase my velocity to 1, 2, 3, 4 over some interval. So is my acceleration positive or negative? Positive. Am I speeding up or slowing down? Speeding up. How do you know that? Talk to one another. I heard lots of tables whispering, wow, because the acceleration's positive, that means speeding up. I'm going to let you just sit with that for a second, but you should probably know by now, by the tone of my voice, that this means that there's a trap ahead. Okay, so then this object changes velocity, comes back to 0 velocity. For that interval, for that section of the line, is the acceleration positive or negative? Negative. Now you're all nervous. Because I told you there's a pitfall trap. It's negative. Of course it is. How do you know that? Slope of the line is? Negative. The acceleration's negative. Are you speeding up or slowing down? Let me be more helpful here. There's 0 velocity. Oh, I just heard a light bulb go on. I didn't get to see it because I was looking the other way, but I just heard one go twinkle, twinkle, twinkle. Hopefully it didn't pop yet. Okay, so is it speeding up or slowing down? For that segment, where do we end up with our velocity at here? 0. So we went from some non-zero velocity to zero velocity. Went from a positive non-zero velocity to a zero velocity. That means we're slowing down. We were going, now we're not going. That's slowing down. Now, over some interval of time, I change my velocity again. Is the acceleration during this segment, oh, I saw another light bulb go on. Is the acceleration during this segment positive or negative? Don't yell it out, talk to one another. Slope of the line is blank, therefore acceleration is blank. Oh, I heard another light bulb go on. Slope of the line is negative. That acceleration in that segment of line is negative. Is this object speeding up or slowing down? Here's the trap. Speeding up? Sean Garza, are you crazy? How can it possibly be speeding up when it's got negative acceleration? Please explain.
Speeding up backwards.
Yes. And we don't know which way the front of the car is pointing, but it has got an increasing negative velocity. The magnitude of the velocity is increasing. Nobody likes this. It's okay. You can hate this. Nobody likes this. The magnitude of the velocity is increasing. If we take the absolute value of the velocity, yes, it's in a negative direction, but the magnitude of the velocity is growing.
So it's like
It's going away from zero in a negative direction. Nobody likes it, Brady. You don't have to like it. It's just the way it is. So now, over some interval, this same object, you know what's coming next, of course, does that. So, once again, is the acceleration positive or negative? Is it slowing down or speeding up? It is slowing down because its velocity is approaching zero. It's positive. So we have positive acceleration and an object that is slowing down. Ah! Cats and dogs living together. Mice making treats for kitties. Frogs falling out of the sky. No, it's not that dire. When you're looking at a velocity time graph, you have to be cognizant of the magnitude of the velocity. Be aware of the magnitude of the velocity. Trust that slope piece. When I ask you, is this a positive or negative acceleration, look at the slope. Okay, do you have questions? So the question that was brought up, and I'll get rid of, let's do one of these. Oh, hey, I could use a line and make actually decent graphs. What a novel concept. There, okay. The question that was brought up was, if an object has zero displacement, is its velocity always zero? Yes, over the long haul. So if we look at a position time graph for an object that behaves as follows. Starts at origin, goes to here, 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 and then ends up here. Let's do our little line here. Whoops. Ah! Whoops. Okay. For any one of these segments, we can look at that segment. Well, displacement, this is what, 1, 2, 3, this is 4, 0, 1, 2, 3, 4, 5, 6, 6, 7, 8, 9, 10, 9, 8, 7, 6, 5, negative 3, back to 0. Okay, we can look at that segment from position equals 0 to position equals 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can say that V average for that interval, well, final position is 4 minus 0 divided by 9 seconds. So we would have, roughly, what, a half meter per second? That's different than if we looked at this interval. The fact that you had to backtrack lowers your overall average velocity. If we looked at, if we looked at the interval from second equals 0 to second equals whatever, average velocity for the entire journey here is 0, because you're right back where you started. And that is an important point, that as long as you come back to the point that you started at, doesn't matter how you got there, your average velocity is 0. Okay. Doesn't matter if you're going 120 kilometers per hour. If you're not changing your velocity, you're not accelerating. So constant velocity, and that becomes really, really super important in a couple chapters. Constant velocity means 0 acceleration. Now, if we look at the position time graph, are there any points here where the velocity is, where here is the velocity 0? Yes.
From 0 to 6, and also from 6 to 4.
Is the velocity 0? So let me change this line a little bit. Let me muddy up the water here, or unmuddy it.
Acceleration.
So this is a position time graph. Slope of the position time graph gives you what? Velocity. Where on this is the velocity equal to 0? Where is the slope of the position timeline 0? Right there. If we were, measuring very carefully at that exact point when it turns, there's probably a moment of 0 velocity as it turns around and moves backwards. But the slope of this line gives velocity. The slope of this line, the slope of this line gives velocity. Yeah, the slope of this line gives acceleration. Do you have questions? I couldn't tell if that was a nod or no? Okay. You good? Okay. Very, very quick little recall quiz. It should be about as easy as yesterday's was. Let's do practice problem 2B, and then we will, I'll cut you loose to work on the book problems. Shuttle bus slows to a stop with an average acceleration of negative 1.8 meters per second squared. How long does it take the bus to slow from 9 meters per second to 0 meters per second? In other words, what's the time that it is required for this bus to stop? So what we know is that average acceleration over any interval is equal to the change in velocity divided by the time interval. We want the time. This is what we're solving for. Oh, you know what? I can't believe I did that. Average acceleration, change in velocity, delta t. Let me move those up just a little bit. Oopsie. Sorry. Jeez Louise, Moser, come on, get it together. Okay, so I'm gonna set aside, pretend that I didn't write the equation yet. I want to list my variables. So we're given the average acceleration, negative 1.8 meters per second squared. Delta V. Well, delta V equals VF minus VI. Are we given either of those? Yes. Which one? Both. What's the initial? 9 meters per second, 9.0 meters per second. The final is 0. And I will warn you that a lot of these questions will say either, comes to a rest, comes to a stop, in which case final is 0, but they didn't say 0, or they'll say starts from rest, in which case initial is 0, and that's a common thing to miss. Okay, so we've got our final and our initial. Delta t is what we'd like to know. So we know that acceleration is equal to delta v over delta t. Here's the amazing part, Midvale varsity team. Many of my smartest and best students struggle when solving for the denominator in three-part algebra. I'm just reporting the facts. 13 years of teaching, 10 years of teaching physics. Smartest kids do the dumbest stuff with three-part algebra. If you tend to do the dumbest stuff with three-part algebra, do it the long way. Delta T A average equals delta V. Divide both sides by A average, and hey, lo and behold, there we are. Okay? It's okay to go around the barn. I'm not going to think less of you. Now we know that delta V equals VI, or VF minus VI. So delta T equals VF minus VI over average acceleration. Seriously, Moser, do I have to write VF minus VI? That's ridiculous. Why don't I just write a number in there? Why are you wasting my time? Because this is three-part algebra. Wait till we get to 16-part algebra with trig functions. Yes, you should write it all out until you have an equation that exactly solves for the thing that you're solving for with all variables. Don't take shortcuts. I see you looking squirrely. Okay, excellent. So delta T equals 0.0 meters per second minus 9 meters per second divided by our acceleration of negative 1.8 meters per second squared. Should we do a little bit of dimensional analysis because I know how much you enjoy it? So our answer should be in seconds. We have meters per second divided by meters per second squared, which would be invert and multiply, so seconds squared over meters times meters per second. Goes away, goes away. Hey, it works. Okay, we rearranged it right. If you're one of those kids on the Midvale varsity team who struggles with three-part algebra, dimensional analysis can save your life. So what do we have? We have negative 9 divided by negative 1.8 meters per second squared, negative 9 meters. Okay. What do we get? 5. How many sig figs do we have? 2. Okay, it gave us everything with 2. So when you've got 2 sig figs, you need to make sure you put 2 sig figs in. Even though the number comes out as 5, that is 5.0. Make sense? Seem logical? Oh, by the way, if you're updating your little note card and you've already got V average equals delta x over delta t, now might be a good time to put in the fact that acceleration average equals delta v over delta t. I would put that on there. Okay, work on the 4B book problems. I will get, if you finish those, I'll give you the worksheet. If not, you'll get the worksheet on Monday.